Howdy. So I was looking around today for some graph theory theorems that might make good videos, and I found one that's very accessible, but it does exhibit a little bit of mental gymnastics, and I'd like to show that to you now. Alright, so the theorem is that G is bipartite if and only if G contains no cycles of odd length. Alright, so let me give you a definition. First definition is a little piece of notation in a graph. If nodes A and B are linked, I will be saying that A, B is equal to 1, otherwise A, B is 0. What does it mean for G to be bipartite? The nodes of G can be separated into sets A and B such that no two nodes of A connect and no two nodes of B connect. So this is saying A prime is 0, A and A prime are not connected, B and B prime are not connected for all A and A prime and A, and for all B and B prime and B. Alright, so that's what it means to be bipartite. So, in order to tackle this theorem, let's give these two statements some symbols. I'm just going to say B is the statement G is bipartite. Alright. And O is the statement G has a cycle of odd length. And this is going to enable us to think about our theorem at a high level. So what our theorem says is that B, if and only if not O. Alright, so that's our theorem. So let's tackle the forward implication first. Alright, which is B implies not O. So a graph is bipartite necessarily means that it does not contain a cycle of odd order. Well, proving a negative is hard. So let's flip this around. This statement, if and only if O implies not B. That's actually a bit easier to show. So we assume O. So we assume that G has a cycle of odd length. So suppose O. Let in 1 through nk be a cycle of odd length. Let's try to separate, try to partition in such a way that this partition of n1 through nk fits this criteria here for G to be bipartite. Without loss of generality, the first node in our cycle, well, first it's one of the nodes of our cycle, is an element of A. Since this is a cycle, N1 connects to N2, N2 connects to N3, and so forth. So since N1 connects to N2, and for one of these sets, all of the things in the same set have to be disconnected. So these can't belong to the same set. All right, N2 is in the other part of the partition. Similarly, N2 and 3 is equal to 1, so N3 is an element of A, and dot 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 in K is an element of A since K is odd. Well, since in 1 and K, in 1 and K are connected, cycle, we have a contradiction. All right, we have shown that G is not, well, not really a contradiction. We have shown G is not bipartite. All right, so we've shown the forward implication. All right, let's move on to the backward implication. So backward implication would be not O implies B. All right, there are no cycles of odd order. Let A be a node of a component of G. So if G is this graph here, this graph has two components, two connected components, right? So we're sticking inside we're picking a connected component and picking a node of that. Now also generality, let A be a member of the first partition. For all B such that A, B are connected, let those B's be part of the second partition. Now, B prime is equal to 0. None of the B's are connected since we're assuming there are no odd cycles, and if any of the B and B primes are connected, this is an odd length cycle. Okay. For all C such that BC are connected, let C be an element of A. C prime So either both the C and C prime are connected to the same B, and that's a cycle of odd length, or they're connected to different B's, but the B's are all connected to the same A. That's a cycle of length 5, and we know by assumption there are no odd cycles. And so on for all nodes in the component. Similarly, for all components, all right. Now take one of the sets of each component, combine them together. You've got one component of your bipartite decomposition of the set G, and then all the rest form the other part of the decomposition of the set G. And so we have proved what we set out to show, that G is bipartite if and only if it contains no cycles of odd length. Alright, this was a fairly short and straightforward video just to get me back into the swing of things. My plan is for my next series of videos to start with no experience required and work up to the fact that every principal ideal domain is a unique factorization domain. So a deep dive into abstract algebra, which I'm really doing for myself as it's my worst subject. All right, thank you for watching.